Hello everyone, welcome to the next lecture of electronic devices. We are covering chapter number 4 on diodes, and this is lecture number 3. So by now we have introduced the concept of what a diode is, how it can be used for rectification or making logic gates. We also talked about forward and reverse biasing. We looked at its ideal IV characteristics, nonlinear. Today, in this lecture today, we are going to specifically talk about what is inside a diode, why does it have nonlinear characteristics, why does it start to conduct at a specific voltage value. For an ideal diode, we just said that it's going to start conducting at 0 volts, which is not true. Of course, for a real diode, it will start to conduct at a specific voltage. So we are going to discuss more details on exactly what's inside it and how does it work. Okay. So diode is a semiconductor. Diode is essentially a PN junction. We will discuss more what is P and N in a PN junction is. So anyways, I'm going to give you a quick brief introduction to semiconductors, how we make these devices, and if you are interested in more details, please take the next version of the course, Physical Electronics. That will give you much more details of the physics behind semiconductors. Okay. So today we are gonna discuss this brief introduction to semiconductors, how we make diodes, PN junctions, and that will also form the basis of your subsequent chapters of transistors. Because essentially we're going to use the same semiconductors, these PN type materials. We're going to talk about that, what those are, but we will use similar things to develop these transistors as well. And we're going to get back to which we will discuss in the later chapters. Okay, semiconductors. So most of the semiconductors that you can see in your electronic instruments or computers, iPhones, they are mostly made up of silicon. So let's look at the silicon atom. Silicon atom has 14 electrons. Right. So 2 in the first shell, 8 in the second shell, and 4 in the third shell. So this means the valence electrons. There are 4 valence electrons in every silicon atom, right? And how many does it need to make into a stable orbit? It needs 8, right? So 4 are missing. So what will happen? So this is in a silicon atom. In a silicon crystal, we have many these silicon atoms combined together. So how do they make a stable silicon crystal? So in a silicon crystal, in order to make everything stable, what every atom does is every silicon atom shares their valence electrons to form covalent bonds. And I'm going to show you an example how they do that. So just imagine this is a silicon atom. It has these 4 valence electrons. Here's another silicon atom, 4 valence electrons. Here's another silicon atom. Right? So this electron pair will be shared to form a covalent bond. For example, there could be another silicon atom over here. And as you can see now, another silicon atom over here. And of course, this process continues in all directions. Right? So this process continues in all directions. And now you can see by making these covalent bonds with the nearby silicon atoms, with the nearby 4 silicon atoms, every silicon atom has 8 electrons, 4 shared and 4 valence electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8. right? So that is why it can kind of form a stable silicon crystal in which every silicon atom shares the valence electrons to form covalent bonds with the nearby other silicon atoms. Now I'm going to introduce another excuse me. I'm going to introduce another term, intrinsic and extrinsic crystals, or intrinsic and extrinsic semiconductors. We're going to start to use this term more and more often in this chapter, in the subsequent transistor chapters as well. Okay, so what is so let's define what is an intrinsic silicon crystal. So at low temperatures, all covalent bonds are intact and no electron is available to conduct current, right? For example, if we look at the silicon crystal, which is composed of, again, silicon atoms sharing nearby electrons to form stable bonds, covalent bonds. So what happens is, if it's just silicon and we are not adding any other impurities, it is called as an intrinsic silicon crystal. We're going to also see shortly that there are certain extrinsic semiconductors in which we will add certain other impurities to generate these extra charge carriers. Okay, let's again go back to silicon crystal. We have a silicon crystal which is stable. Stable in a sense that we have silicon. Every silicon atom shares these 4 electrons in a form of a covalent bond with the nearby silicon atoms. So at so at low temperatures, all of these covalent bonds are intact, and this entire crystal does not have any majority charge carrier, any electron available to conduct the current, right? So this will behave like a neutral thing. So no charge carriers are available to conduct any current. Now, interestingly, what happens is, as temperature increases, or for example at room temperature, thermal energy breaks the covalent bonds in a process called thermal generation. It produces a free electron which conducts in presence of electric field. Right, so by now we talked about at low temperature, all the covalent bonds are intact and there is nothing available for the conduction to occur. However, as temperature increases, for example at room temperature, there is sufficient thermal energy available that is going to do is going to break down these covalent bonds. And now as these bonds will be broken down, it is going to produce a free electron. Right? One of these electrons will be free, and that electron can potentially conduct, as we're going to apply an electric field. So if we apply an electric field, that electron will start to conduct. So at higher temperatures, as more sufficient thermal energy is available, it is going to break these bonds and electrons can be produced. So for example, if this silicon atom is going to, for example, if by the breaking of the covalent bonds, for example, if this silicon atom is going to give this electron as a free electron, what is going to happen to this silicon atom? This silicon atom is going to get only 3 electrons here, and it will produce something that is called as a hole. It is going to have a lack of 1 electron, so that will generate something that is called as a hole. Right, so this is a hole. So in terms of thermally generated free electrons, are equal to the number of the holes that are created. So number of holes and electrons are equal in intrinsic semiconductors. All right. So let me write this thing down as well. Right. So the free electrons creates a net positive charge on parent atom, which provided the free electron, called as hole. Which can also move around the crystal. So number of electrons equals number of holes. Okay, right. So what we discussed now is we have a silicon atom, a silicon structure at low temperatures. Everything is there. All the covalent bonds are intact. There is no charge carrier for the conduction to occur. However, as temperature increases, these bonds can break down. A silicon atom can release one of the electrons, valence electrons, as a free electron. When that electron will be removed, will be released, we're gonna get a net positive charge on that silicon atom like this. And that positive charge is known as a hole. So the number of electrons, free electrons, and the number of the holes in intrinsic silicon crystal are the same. And both free electrons and the holes can conduct in the presence of an electric field. All right, now let's talk about extrinsic semiconductors. Extrinsic semiconductors. This is also known as doped silicon. Silicon being an example of a semiconductor. So we also call extrinsic semiconductor as doped semiconductor. Doping is a process in which we add impurities to the semiconductor, right? So doping is a process to add impurities to intrinsic semiconductors. So in intrinsic semiconductors, we add these extra impurities, and this process is known as doping. So those semiconductors are known as doped or extrinsic semiconductors. Okay, now if we add a trivalent impurity, a trivalent impurity is the one which has 3 valence electrons, right? So trivalent impurity has 3 valence electrons. For example, example could be boron, right? So every boron atom in the valence shell has only 3 valence electrons. And how many valence electrons do we need to form a crystal? To form a to complete the orbit? 4. So essentially what do we have? We have one less electron available. So that will result in generating a hole. Okay, so now this is, let me if we add a pentavalent impurity now, right? So now rather than adding a trivalent impurity, let's suppose we add a pentavalent impurity to a intrinsic silicon to make into an extrinsic silicon. If we add a pentavalent impurity, it is going to have 5 valence electrons, right? We just need 4 to complete the orbits, right? to create those covalent bonds and complete the orbit. So if you just need 4, there is 1 extra electron now available. Example of the pentavalent impurity is, for example, could be phosphorus. So now what we get is we get 1 extra or free electron. All right, so these are also known as, right, so these trivalent impurities are also known as accepted impurity, right? So it has 1 less electron, so it needs 1 extra electron, so it's an accepted impurity. And these type of extrinsic semiconductors are also known as p-type. And similarly over here we have 1 extra electron, so these are known as n-type semiconductors. And these impurities are known as donor impurities. It has 1 extra electron to available, right? So these are donor impurities. All right. All right, so before we will move forward, again, we have intrinsic semiconductor, right? So intrinsic semiconductors, all the bonds are stable. No charge carriers are available for conduction to occur as the temperatures are increasing. Now you will realize that we are talking about 2 different charge carriers. As the temperature is increasing, some of the charge carriers are being produced by the breaking of these bonds and creating a free electron in a hole. The number of the free electrons in the holes are the same in intrinsic semiconductors. What is happening at the extrinsic semiconductor? Now we add more impurities, these extra external impurities as well. If we add a trivalent impurity, it becomes a p-type material, and there is a lack of electron, 1 less electron, so it is going to have a lot of these holes as majority charge carriers. And if we add a pentavalent impurity, it is going to have 5 valence electrons, so it is going to have one extra electrons for the conduction to occur. So this is known as an n-type impurity. I'm also using 2 different terms, and we're going to use that. One is majority charge carriers. Majority charge carriers comes with this and comes due to doping. And one is called as minority charge carriers. Right, majority charge carriers are because of this doping. Because when you add a trivalent impurity, you have a lot of holes as majority charge carriers. When you add a pentavalent impurity, you have a lot of these electrons as majority charge carriers. Minority charge carriers are these thermally generated carriers. We discussed that in the intrinsic, whether it's an intrinsic or an extrinsic semiconductor, as the temperature increases, the bonds will break, and that will generate electrons in the holes. So those are minority charge carriers. Okay. So next we will talk about, let's come to the diode now. What is up with the diode? So diode is a PN junction. So we're going to talk about PN junctions now. Right? So what is the PN junction? P and N. We talked about p-type materials and n-type material. So essentially, this is P and N type combined, not essentially combined together, but side by side. So what do we do is, let me actually make a structure and then I will talk about it. So this is how a PN junction looks like. This is anode. This is cathode. This is p-type silicon. This is n-type silicon. Now you can see that the p-type and the n-type are side by side. So this makes a junction which is known as PN junction. So this is the PN junction, and this is essentially what a diode is. And we will realize that when we're going to make transistors, and they also have this P and N in different configurations, P and N type materials in different and different configurations. So this is very important to understand. Okay, so before I start talking about how the conduction happens in a PN junction and in a diode, one quick thing is PN junction is not created by combining the p and n-type materials together. What will happen is we always start with the same silicon crystal and have different dopings, p-type doping and n-type doping on the same crystal, right? So PN junction is created by doping different regions on the same crystal, same silicon crystal. So we use the same silicon crystal and then dope p and n-type together at the side side by side on different regions of the silicon crystal. All right, okay, so this is what a p-n junction is. We have p-type and n-type on the sides. All right. So let me show you a slightly more detail what is happening here, and then we will talk about how this is happening. Again, we have anode and we have cathode. Again, this is a p-type material. This is an n-type material. We know that in a p-type material we have a bunch of holes. Holes are positive charge carriers. And in an n-type material we have a bunch of electrons. Electrons are negatively charged carriers. And then what do we get over here is I'm going to talk about shortly what this is. All right. So what did I draw? Now I'm going to discuss that in details. Okay. So first, let's start with the very first thing. The very first thing is that we know that in a p-type material, our concentration of holes, positive charge carriers, is very high, and in n-type material, our concentration of electrons is very high, right? So the very first thing that will happen is the process that is known as diffusion. The electrons will start to move from n-type to p-type, and the holes will start to move from p-type to n-type, and it will constitute a current that will known as a diffusion current, right? Okay, so let me write this thing down. So concentration of holes is high in p-type than n-type region. Right? So we have a lot of these holes here in the p-type than the n-type region. So holes will start to diffuse into n-type region. Similarly, electrons will diffuse from n-type to p-type. This is called diffusion current, ID, right? So the diffusion current will be from following the conventions. Here is the diffusion current, direction of the diffusion current. All right. So what do we have is, again, we have the very first thing, we have a bunch of these holes in the p-type, a bunch of electrons in the n-type. So a simple diffusion will start to take place where the holes will move from the p-type to n-type, right? So these holes are moving from p-type to n-type, and the electrons will start to move from n-type to p-type, and this will constitute a current that is known as the diffusion current. I'm going to shortly come back to what is this region in the middle with positive and negative charges here. Now, while this entire process is happening, okay, so let me first tell you, and then I can write it now, right? So again, the first step is simple diffusion. holes are moving from the p-type to n-type. Now what is happening while the holes will move from, so what will happen is, as these holes will move from p-type to n-type, they will, as the holes from p-type to n-type comes to the n-type, they will combine with the electrons, right? So if a hole will combine with the electron, it will neutralize. And now some of these holes will combine with the free electrons that are available near the junction of the n-type, and it will create a region that is depleted of the electrons, and that is why we have these positive charges near the junction appearing over here. Now let me write this thing down as well. So as holes moves from p region to n-type region, they recombine with electrons, with majority electrons. By majority is the majority charge carriers, majority electrons, and neutralize. Now some of these holes will also combine with the free electrons near the junction vicinity. And create a region which is depleted of electrons, right? A positive region. Right, so again what is happening is our p-type, the holes in the p-type are moving to the n-type region, and as they are moving, the holes will recombine with the electrons and neutralize. However, as these holes are moving to the n-type, there are some free electrons present as well in the near the vicinity of the junction. Near the junction over here, right over here, there will be some electrons that are present. These are the free electrons. And what will happen is these holes, these positive charge carriers, when they will recombine with these holes, with these electrons, sorry, they will again neutralize. But as they get neutralized, we know that we have these electron hole pairs that were created. So we have these leftover holes near the junction, and that is why near this vicinity we have our positive charge carriers left. And similarly, now what is going to happen at the same time is our majority charge carriers are diffusing from electrons, which are electrons in the n-type. So our majority charge carriers, electrons from the n-type, are diffusing into the p-type region. These electrons will recombine with the holes and neutralize. However, these electrons will some of these electrons will recombine right at the junction where we have a bunch of these positive charge carriers near the vicinity of the junction. These electrons will combine with those holes as well and recombine. Recombine is a recombination process, is a combining of the holes and electron pairs to neutralize. So anyways, these electrons, while they are diffusing into the p-type region, at the vicinity, they will recombine with holes and neutralize. Plus, while that neutralization process is happening near the vicinity, what will be left will be the negative electrons, again because of the electron hole pair that was created. So if some of those holes were lost in the recombination process, we are left with electrons. So that is why you have a negative charge appearing over here. Okay, so I can write this thing as well now. Similarly, electrons move to p region and combine with holes and neutralize. However, near junction vicinity, more holes will be neutralized and a region is created which is depleted of holes, right? And that region is a negative region. So this is how this region is created, right? This entire region. Okay. All right. So if you look at this region closely, this is an interesting region because it has positive and the negative charges there, and it essentially creates a barrier. And this region is known as a depletion region as well. So this creates a barrier or a depletion region. And an electric field exists in this region and a barrier potential. Now, from here you can see that we have an electric field that exists over here in this direction because of this region. This region is known as a depletion region, a barrier region. This is also known as a barrier potential. And now you will realize that for any further conduction, this will stop any further conduction. And in order for any conduction to occur, we need to overcome this barrier potential. So this barrier will stop this barrier will stop the holes to diffuse into N region and electrons to diffuse into P region, right? And we need to overcome this barrier potential to conduct across PN-junction. All right, so let me give you a quick summary of what we have talked thus far. Right, so we talked about intrinsic and extrinsic crystals, intrinsic and extrinsic semiconductor, doping. From the process of doping, we create a p-type and n-type materials. Now, these two materials sideways can create a PN-junction. This PN-junction is a diode. Now, p-type material has a bunch of these holes as majority charge carriers, as we discussed earlier. N-type material has a bunch of these electrons and majority charge carriers. So as soon as these two are present sideways alongside with each other or combined together, a diffusion current will start to flow. What will happen is holes which are in high concentration in the p-type material will start to diffuse into n-type, and electrons will start to move from n-type to p-type. Now this diffusion currents will start to happen. Now as this diffusion current is happening, let's take one case first, what is happening in the p-type. These holes that are moving from the p-type to n-type are combining with the electrons in the n-type and neutralizing. Now some of these holes will combine with the electrons that are present near the vicinity, and as those electrons will be recombined and neutralized, what we will be left with is with the holes near the vicinity of the junction. That is why we have a positive charges here, And a similar process happens to create a negative potential on the other side of the junction. How does that happen? Our electrons are moving from the N type to the P type. They will recombine and neutralize. More electrons, more holes will be neutralized near the vicinity of the junction, and we are left with these extra electrons. And that is why at the barrier we get this negative charge here. Now, if we look closely at this region, this is a depletion region. This is also known as a barrier potential. And now, if we look closely, we can see that this potential will prevent any conduction to occur further. Because of this potential, our holes will not move from the p-type to n-type, or our electrons will not move from the n-type to p-type. So what do we need to do is we need to, if we want the conduction to ever occur, we need to overcome this potential, this barrier potential, or we need to overcome this depletion region. And this is where the forward and the reverse biasing of the PN junction will come in. So I'm going to talk about that in a second. There is one more thing before we talk about the forward and the reverse biasing. There's another type of a current called as a drift current that is also flowing in the PN junction. This current is negligibly smaller. Okay, so drift current is usually denoted by IS, is because of thermally generated minority charge carriers across PN junction. IS is very small and strongly dependent on temperature, and electrons in P region accelerates in depletion region to move towards N region and vice versa. So let's look at this drift current closely. By the way, this drift current is usually extremely smaller than the diffusion current. All right. Right, so this diffusion current that we initially talked about, the direction of this is over here, right? So this diffusion current is due to the majority charge carriers of these holes and electrons in the P and the N type and diffusing across the junction and creating a barrier. There's another current at the same time that is flowing across the junction, and that is known as drift current. And the direction of the drift current is opposite to the direction of the diffusion current. Please note that this IS, this in terms of notations, right? This is diffusion current, and this is drift current, right? Both starts with a D, but this one is a diffusion current, this one is a drift current. All right. So the direction of the drift current is, so the three important things to note about the drift current IS. So one is, it is because of the minority, because of the flow of these minority charge carriers across the junction. And minority charge carriers, we discussed earlier that they are usually thermally generated. As the temperature increases, the covalent bonds break down, they create electron hole pairs. So we have a bunch of these minority charge carriers that can also flow. And for example, this usually constitutes, for example, in the terms of this drift current, electrons in the p-type region will accelerate across the depletion region to move towards the N region, and vice versa. And that is why this drift current direction is opposite to the diffusion current. Another most important thing to remember is that this drift current is essentially, this drift current is very, very smaller than the diffusion current. And importantly, this is strongly dependent on temperature, because thermally generated electrons, minority charge carriers, are dependent on temperature. Okay. Now we will move towards our next part, which is how we can make the conduction to happen. Again, in order for the conduction to happen, we discussed that we have this barrier that is sitting there. So we really need to overcome this barrier for the conduction to occur. Right? Okay. So let's conduct the PN junction. Okay, so let me go over here. Okay, so we have this positive, 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 negative, negative, negative. This is an n-type material, this is a p-type material, right? So what we will do is, and our electric field exists like this. Right, so essentially in order for the conduction to occur, what do we need is, we need to connect a battery. Connect a battery opposite to barrier potential. Right, okay, so for example, this is a p-type. Our barrier potential is here, this is negative. So if we connect a battery such that positive comes here and negative comes here, we will realize that we can start the conduction to occur. Current is going in this direction. And if you also realize, right, since this terminal is anode and this terminal is cathode, this is the same as forward biasing the diode, right? So this is equivalent to forward biasing the PN junction. Okay. Let's call this as source voltage or input voltage. Now, if you look at the potentials closely, the Vs is in the direction that subtracts the barrier voltage. Let's call the barrier voltage V0. So what will happen is, what do we get across the PN junction is essentially V0 minus Vs. So this results in reduced barrier voltage. So as we will increase Vs, our barrier voltage, we will start to decrease the barrier voltage. Now, as Vs approaches V0, right, as Vs will approach to V0, barrier voltage reduces negligibly smaller, and PN junction start to conduct. And we know that the total current that is going to flow is the diffusion current minus the drift current. And we already know that the drift current is very, very smaller than the diffusion current. Okay. So the important thing is that by forward biasing the PN junction, we can make the conduction to occur. So how we can forward bias it? In a very simple process, we want to make sure that we are connecting the battery in opposite to the barrier potential. So if we connect the battery in opposite to the barrier potential, the potential across the PN junction will be such that it is these two potentials will be subtracting, so our overall barrier voltage will start to reduce. And now as this Vs will increase, our barrier potential, right, so as this Vs will increase, our barrier potential will start to reduce, and we will see that a point will come when Vs will become equals to V0. And when Vs will become equals to the barrier potential becomes negligibly smaller, and the conduction will start to happen. what was happening, we had a good amount of a drift current here. But we ended up establishing this depletion potential. That is why the conduction also stopped. And we did not have any external source as well. So if we want to have a conduction occur across the PN junction, we will apply a barrier potential. We will apply an external source opposite to the barrier potential. And as soon as that source voltage will become equal to the barrier potential, the conduction will start to occur. And so this is known as a forward biasing the PN junction. This is also known as forward biasing the diode, right? So our diode was this. And we saw that, initially we saw that what will happen is, this was a VI characteristic, right? We saw that, okay, when this is 0 volts, nothing is happening, and then the conduction will start to occur. Now, essentially, this is not true. So what will happen is, there is a barrier potential, and the barrier potential is around, let's say, 0.7 volts. The conduction usually start to occur at 0.7 volts, and then at 0.7 volts, we get a large peak of this current. So this is more of a real diode model. Actually, a real diode model is slightly more complicated. It has an exponent rather than, again, this step function. It is going to have an exponential function. We're going to talk about that in the next lecture. We're going to come back to the diode model again in the next lecture. Okay, let's quickly talk about reverse biasing a PN junction. Okay, again you have this P-type, N-type, and let us suppose now if we connect it in the opposite direction, right? Now the anode is connected to the negative terminal and cathode is connected to the positive terminal. We saw that this is reverse biasing the diode, which is essentially a PN junction, so reverse biasing the PN junction. Let's call this as Vs, and let's call this barrier voltage as V0. Now we see that the Vs is in the direction such that it adds to the barrier voltage. So V0 plus Vs. So the effective barrier voltage increases and PN junction does not conduct, right? So if we will reverse bias the PN junction in this way, then our effective barrier voltage will increase and the PN junction will not conduct, right? So that is why we say that, okay, reverse biasing the diode is going to behave like an open circuit because it's not conducting at all. All right, there's one small concept that I want to talk about before we end this lecture today, and that is known as a breakdown or avalanche. So what will happen? So breakdown. So what will happen if we continue to increase this Vs in the reverse bias condition, right? So with increased reverse voltage, right? So in a reverse bias condition, the Vs is the reverse voltage. So if we continue to increase the reverse voltage, right? So the electric field intensity will increase. Electric field of the barrier increases of the barrier. And minority charge carriers gets more kinetic energy and knock down the bonded electrons, right? Essentially, they will break down the covalent bonds and they will knock down those electrons. This will increase the drift current tremendously in opposite direction. So this, at the voltage at which this thing happens, is known as a breakdown voltage, and this effect is known as an avalanche. We will see how, when we are going to talk about again the real diode IV characteristics, we will also talk about the avalanche effect again. Okay, so this ends our lecture. I'm just gonna give you a very quick recap before finishing up this lecture. Right, so we started with the semiconductors, the silicon atom. Most of these PN-junction semiconductors are made of silicon. They could be made by other semiconductors as well, for example germanium. So anyways, we studied silicon. It has 14 electrons, 4 in the valence. So in order to make this in a silicon crystal, every silicon atom is sharing these 4 valence electrons with the neighboring silicon atoms through covalent bonds. And all of these covalent bonds will remain intact at low temperatures. However, as temperature increases, these bonds will break down, and a single silicon atom can, one of the valence electrons of that single atom can become free, and as it departs, a net positive charge will appear on the silicon atoms. So this creates a kind of an electron hole pair. So number of electrons and number of holes are the same in intrinsic silicon. Now what will happen is, when we add impurities by a process known as doping, we create extrinsic semiconductors. So if we add trivalent impurities, for example boron, the 3 valence electrons, of course we are giving a lot of these holes, so we have 1 less electrons available. So we're gonna have a lot of these holes as a majority charge carriers. However, when we add a pentavalent impurity with 5 valence electrons, we're gonna have a lot of these electrons as majority charge carriers. Then we talked about making a PN junction, p-type and n-type together. So what will happen is, the first 2 types of current will flow. One is the diffusion current, and diffusion current is the main current that will flow. Now in a p-type, we have a bunch of these majority charge carrier souls. They will start to diffuse into the n-type region. As they are diffusing, they will recombine with the electrons and neutralize. What is happening at the vicinity of the junction is, more and more of these electrons are being neutralized, and what we are left with is with the holes near the vicinity. So we get a layer of these positive charges. And the similar process happens for the electrons in the other direction. We get a negative charge, so we create this barrier potential or a depletion region. So in order for the conduction to occur, we really need to overcome this barrier potential. And this is where our forward and the reverse biasing comes in. So if we apply the source voltage or the input voltage is in the opposite direction to the, for example, if the anode of the PN junction is connected with the positive terminal and the cathode with the negative terminal, right? Or if the battery, or if we bias the PN junction in the opposite to the barrier potential, then these voltages will essentially kind of subtracting out. So as we increase the Vs, the barrier voltage reduces. Once it will reaches to the level of the barrier voltage, the depletion region becomes negatively smaller and the connection will start to occur, where the total current will be ID minus IS. Similarly, in a reverse bias condition, we connect a battery opposite in the opposite direction to the forward bias, where our anode is connected to the negative, cathode is connected to the positive. Our in Vs voltage or battery is in the same direction as the V naught. So the barrier voltage is kind of effective barrier voltage is kind of increasing now. So the PN junction will not conduct. And the last thing that we discuss is the breakdown, that as we are increasing this reverse biased Vs voltage, we will continue to increase it, the electric field that exists in the PN junction. will increase, and that will give more and more kinetic energy to the minority charge carriers. They can easily knock down those bonds, covalent bonds that were sharing the electrons. So the electrons can be knocked out. Once the electrons are being knocked out, this will increase the drift current tremendously, and that process is known as an avalanche effect. And the voltage at which this thing will happen is the breakdown voltage. All right, so this will finish up our lecture, this lecture, and the next lecture we're going to talk about the IV characteristics of a real diode. All right, so with that, thank you so much. I will talk with you in the next lecture. Bye bye.